Mutual Information. My name is DJ. In this video, we're going to learn about the Fisher information. This thing is an absolutely foundational idea which quantifies the amount of information an observation carries about a parameter. More generally, it provides a general framework for reasoning about parameter uncertainty. It is a frequentist concept, which is kind of a dirty term these days, but it has grown beyond that world. Bayesians and machine learning practitioners love to borrow it for new ideas. To name a few, it's used in the Jeffreys prior, natural gradient methods, experimental design, and probably others that I just haven't heard of. So, to empower you with this idea, my approach will be to explain the goal of the Fisher information and then show how it's a clever way to achieve that goal. Now, for the sake of a gradual explanation, I'm going to start in the simple one-dimensional case and then generalize to higher dimensions. The higher dimensional case is really what you want for applications. That's where all the cool stuff happens. That said, let's jump in. First, let's say a random variable y is related to a parameter, which is just a single number here, by some known probability density function. We write that generally with this expression, which is here to represent any function that accepts both an observation of y and a parameter value, and then gives us a number which tells us the likelihood of that observation according to that parameter. Now, here's the question. According to whatever this thing is, how well does an observation of y locate the parameter value that produced it? In fact, the goal is to measure how well an observation locates that parameter. Now, if you're like me, the vagueness of this goal makes it hard to imagine what a solution would even look like. But what does help me is to consider cases at two extremes. For the first case, let's use the normal distribution with a large variance. What I mean by that is P of y given theta is the normal density function where our theta is the mean of the normal, and we assume we know the variance, which we'll set to a relatively high value of 25. For the other case, we'll consider the exact same thing except with a small variance of 1. Very, very frequently, when we want to go from observations to parameter estimates, we consider the log likelihood function. To show that, I'm going to simulate data according to the large variance case first, and then for each observation, draw the log likelihood function. Each one of these lines tells us how likely one of our observations is as we vary our mean parameter along the horizontal axis. Keep in mind, the data is generated according to some parameter value which I haven't told you. We'll call that value the true parameter value. Naturally, let's consider the small variance case as well. Okay, now, take a step back and look at these two cases. I have not told you the true parameter value, but you tell me, in which case would you have an easier time guessing that parameter value? Isn't it obvious? It's clearly the right side, the small variance case. Effectively, each line shows one observation's vote of where the true parameter is. In this case, all observations overlap on a narrow range, making it easier to pinpoint that value. As you may be able to guess, that true parameter value is 5. Going forward, we'll refer to that true value as mu star. And so, we might say that in the small variance case, our observations provide more information about where mu star is. In fact, I should emphasize, when we say information, it's this narrowness that we're after. Honestly, this view is all you need to understand the goal of the Fisher information. But now, separately, the question becomes, how does the Fisher information turn this narrowness into a number? How do we measure that information? For that, we'll need a new view. First, let's redraw what we just saw. Here, we're showing the small variance case. Next, let's pick a parameter value, totally arbitrarily, to plug into these functions. I'll call this evaluation point mu naught. If we plug mu naught in, we'll get back a big list of numbers. Over here, we'll see an estimated distribution of those numbers. Finally, we're in a position to see the key idea of the Fisher information. The idea is to consider the slopes of these functions at our evaluation point. If we recall a smidge of calculus, we know the functions that generate these slopes are the derivatives, which we can draw as well. In general, the derivative of a log likelihood with respect to the parameters has a special name. We call them score functions. As you can see, in this case, the score functions happen to be linear. As we'll see, all the action hangs out in the distribution of scores at our evaluation point. So, just like we did below, let's show that distribution along with the mean line of that distribution. To get a feel, let's move around the evaluation point a bit. The first thing I bet you'll notice is the shape of the slopes distribution stays the same. Well, please ignore that observation. That comes from the fact that the normal distribution has linear score functions, and that's not true in other non-normal cases. But there is one thing that generalizes to all other cases. when we evaluate these score functions at the true parameter value, the mean of the scores is 0. To provide some real simple intuition, the average score is 0 at the true point because it has to be. If it wasn't, the data would be suggesting a more likely parameter value is somewhere else. But in this setup, that can't be. The most likely parameter value must be our true parameter value because it generated our data. And now we're just about ready to see the Fisher information. But I want you to guess what it is. To help, I'm going to move between our two cases. We're starting in the informative case with a small variance. Now, let's increase it. Getting any ideas? Anything jumping out? It seems to me, in the informative case, there is a wider variance in the scores. In the uninformative case, there is a small variance, which means they are all hanging around 0. To gain some intuition, think about what a single small score value is telling you. If it's 0.001, that means that data point recommends shifting mu by 1,000 if you'd like to increase the log likelihood by 1. If it's minus 0.001, it's saying you need to shift mu by 1,000 in the other direction. So, a lot of score values huddled around 0 collectively tell you to move nowhere, but individually provide wildly different recommendations about where the true value lives. In other words, a small variance of the scores implies a large range of possible mu values. This is the key idea behind the Fisher information. And finally, we can state its definition. The Fisher information is the variance of these score functions when we evaluate them at the true parameter value. In other words, it's a measure of the width of this distribution when it's centered on 0. To put it on the screen, I'll show 2 times the square of the Fisher information as this horizontal width. Now look, as we move between the uninformative and informative cases, the Fisher information follows naturally. And hopefully, you can feel mechanically what's going on. Remember, the goal of the Fisher information is to measure narrowness, and this does precisely that. As we become more narrow, the slopes vary more widely, and the Fisher information increases. But there's more, as you may have guessed from this big empty space. Let's once again consider the slopes at our evaluation point, but this time of the score functions. In fact, in the exact same way the middle row relates to the bottom row, let's create a top row which relates to the middle row. That means we'll plot the second derivatives and an estimated density of the second derivative